Oh, okay. So, okay, guys, let's get started. So, I will briefly read what we learned in the previous class. So, what did we learn? So, we learned how to implement combinational logic, right? So, so actually, in the previous classes, we learned about the Boolean equation, and then we can use Boolean equation to represent some logic. It's called also Boolean logic, right? And then so it means that so we can represent our logic. It means that it's input and output using true and false, right? That's a Boolean logic, right? And then it means we can also represent the Boolean logic using a Boolean equation, right? It's similar to the normal equation, like the normal mathematics equation, like decimal equation, right? So also I mentioned that we need to optimize Boolean equations using some the axioms and theorems, right? So we can optimize the optimization represent we can reduce the terms and then some the terms in the Boolean equations, right? And then in the previous class we learned how to implement Boolean equations using basic logic gate. But it's simple, right? So in the Boolean equation we can also use basic logic gates such as the AND gate and OR gate. So actually in the Boolean equation we use the multiplication and addition symbol operator, just the operator. But actually, these operators are AND gate and OR gate respectively, right? So actually, we can easily implement the Boolean equations using AND gate and OR gate, right? So we learn how to implement the equation using the Boolean, no, using basic gates, and then we also learn how to draw a schematic, right? So schematic means that so we can use the basic gates such as the this AND gate and logic OR gate, and then inverters, and then we can also connect input and output ports of this gate. So using wire, okay, and then this figure, so right, so we just we can just allocate some basic logic gates, and then so actually we can also call this is a module, okay. We can allocate a simple modules, or we can allocate a basic logic gate, uh, and then we we can connect the input and output ports of these modules and basic logic gates. And then this diagram is called a schematic. And then we also learned how to draw a schematic. So certain basic rules for drawing a schematic. Okay, so so as I showed some examples, then so you can also translate the truth table to the schematic, right? And then also a Boolean equation. Also, we learned that all Boolean equations can be represented using SOP form or POS form. So which means that we can implement these Boolean equations using basic logic gate. Okay? Because in the SOP form, we use the AND gate and OR gate, right? So firstly, so we represent the min terms using AND gates, and then we can also connects the output of these AND gates to the input of OR gate, right? This is the SOP form, and then POS form is so we can use the OR gate, so we can use max terms, and then the output of OR gates are connected to the input of the AND gate. Okay. Also, I also explained that we can represent SOP form using only NAND gate. Okay. Okay. And the POS form using only NOR gate. So actually, from the SOP form or POS form, so we can apply the Morgan's theorem, right? So if we apply the Morgan theorem, then we can replace the AND gate to the NOR gate, right? So we can replace OR gate to NAND gate, right? We can replace OR gate with the NAND gate, right? So it means that using only NAND gate, we can represent SOP forms, as also if we can implement the POS forms using only NOR gate, right? So and then also I explained that. So if we use the NAND gates or NOR gate, then we can reduce the number of transistors. Okay. Okay. So here and then I briefly explained, but we didn't have enough time. So I will explain again the X and Z. Okay. So I mentioned that we can use only two kinds of values for the bit data, right? So 0 and 1. But actually, so this is the digital decoupling. So we just restrict some representations using digital manner, right? But actually, in a real circuit, then we can represent some various values or various situations, right? So, but in a digital manner, it's not it. So we cannot represent some these various values or various cases. Okay, but sometimes we need to represent some different values or different situations using a digital manner. So we can use some additional symbols or some additional values. Okay. So X firstly, so we can use the X. So X means the contention. Okay. So what is the contention? The contention means that, so this is the example of contention. So you can, so actually this is incorrect implementation of a circuit actually. So why? What's the problem? The problem is that, so you can find a node, we can observe a node. So this is the same node, right? But this same node, okay, this same node are driven by two outputs, two different outputs of inverter. So I mentioned that this is a driver, okay? Okay, so you can just understand that a driver can generate digital signals, but actually in a real circuit, a driver can provide the electric charge to the capacitor, right? So that's why it's called a driver. So driving means that we can just force a certain values to the output or result, right? It's a meaning of driving, right? So the problem is that the same node is driven by multiple drivers, and then actually, what's the problem? We cannot figure out the exact value. We cannot figure out the exact value of this node. So why? So for example, if this driver, this inverter is driving value 1, and then also the another inverter is driving value 1, then the result, so obviously the output is 1, right? So it means that actually it's a capacitor. Capacitor is connected to the VDD by this driver and then this driver, right? But also if this is the 0 and this is 0, and then the output will be 0. But it's okay. We can figure out the exact value of this node. And what's the problem? If this driver, the driver A is driving value 1, and then driver B is driving value 0, then what will happen? What's the value of this node? We don't know. Okay, we cannot figure out the exact value for this node, but we need to avoid this situation in the digital circuit. What is the system, right? So what's the logic? So logic means that if a certain input, so we need to define a certain input values, and then if a certain these input values are provided to a certain black box or function, that we can get deterministic. We can get deterministic output. That is a logic, right? So actually, for the stable logic, a stable system, we need to define a very clear logic, right? But what's the problem? For this circuit, and then if this driver output is 1 and this driver's output is 0, then you don't know the value. So we need to avoid this situation. And then in order to represent this situation, we can use the X, okay? Symbol X. So X means that it's illegal value, and then it's also, it represents contention. And then this situation is called a contention. It's a contention, okay? It means that a same node is driven by multiple drivers. Okay, so you need to know that we must avoid this situation. Okay. So what is it? So this is the X. So actually in today's class we will learn about the Karnaugh map, but also you can observe the X in the Karnaugh map. So sometimes we can we can use X for representing don't care. Okay, so in a circuit, so we can use the X for representing contentions, right? But we can use X for some different cases. So like the don't care in the Karnaugh map also. So we will learn about the Verilog. So it's the hardware description languages, and then in HDL we can use X for representing uninitialized value. Okay. Okay. So we need to distinguish these different uses of the X. Okay. So if X represents contention, then we need to avoid these situations. But sometimes we can use X for representing don't care value. So don't care means that this value, this bit can be 0 or 1. Okay. So for this case, this is okay actually. Okay. So this is don't. If we just use X for representing don't care, then it's okay. But if we observe contention in a circuit, then it's not okay. 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 So another situation. Another case for in the circuit is floating. So floating means that a circuit is a certain node of a circuit is disconnected. Okay, so it's a floating. So sometimes so it's a switch, right? So if the switch is turned off, so which means that the node P is disconnected from the node A. So if this node has the driver, but this value cannot be delivered to the node B. Why? Because this wire is disconnected. Okay. So, and then this situation. So if this wire is disconnected, then we can represent the value of B using Z. Okay. So it's a certain node is disconnected while it's floating, then we can use this situation using Z. Okay, we can represent this situation by using Z. So it's also called the high Z. So it is because actually this situation, so which means that the wire is disconnected. So which means that it's big. So it's similar to this situation. So this is a certain component, and then the impedance. So or it's also resistance or impedance. So if this resistance is very high, it's like the infinite, and then where this impedance is very high, then we can call this is the insulator, right? Insulator, because the electrons cannot move through this component. Or we can say that this is the disconnected. This wire is disconnected. Okay, so it's like this. So if we just wear a certain glove, and then if the material of glove is insulator, then we can even if we touch this touch screen, but touch screen does not react. Okay, it is because this glove has the very high impedance. So that's why this high Z is frequently called high Z. It means the high impedance case. So you can just understand. You can just understand that high G represent a certain node is disconnected from a driver. Okay. So this is the example. Okay. So this is the example of the for showing the high Z output. So this is the A, so it's a driver, and then this is the enable signal, and this is the output of this buffer. Okay, but so the symbol of this buffer is similar to the normal buffer like A and B, but we can find the control signal E. So this is the enable signal. So and then this buffer is called the tri-state buffer. So it is because based on the control signal, if the control signal is 0, so its enable signal is 0, then Y is disconnected from A. Okay, so you can find the high Z signal here. Okay, and then if the enable signal is 1, then the Y is equivalent to A. So which means that the Y is connected to A. Okay, so this is the tri-state buffer. And then we can implement a tri-state buffer like this, right? So it's a symbol. Actually, it's a little bit different because it's a kind of inverter. But so you can find some control part here. Okay, so it means that the output can be disconnected or so connected to A, so equivalent to the value of A. So this is the dry state buffer. But anyway, so in order to represent this connection case, this connected case, we need to use the high Z. It's a Z. So so actually we can use this logic in a real system. So actually we did not learn about the bus, but bus means there is some communication. So it's a very long wire for communication, and then many components are connected to this bus. So bus shares the communication lines. Okay, but if the problem is that if the multiple nodes are driving the same bus, then this case is the contention, right? So in order to avoid this situation, then we can use the tri-state buffer here. Okay, so sometimes this certain node is disconnected from above this bus, or a certain only one node or one driver is connected to a bus. So in this case, we can use a tri-state buffer, right? So try to understand the different symbol X and Z. Okay. Okay, so and then as I announced, so we will take pubkeys. Pubkeys, it can be translated as the 쪽지시험. Okay, so okay, quizzes. And then, so actually I will activate the quiz on the blackboard. So you can, that's why it doesn't work. So you can access blackboard, but it's not activated currently. So now the quiz is available in the Blackboard. So everyone can access Blackboard. Okay, so if you cannot access the Blackboard, then I also prepared the small piece of papers. Then you can also use these papers. Okay, so and then also you can write answer on the Blackboard. And then I will show the questions. There is the. So this is just the pub quiz. There is the. What is that? You can find the pub on the quiz. So okay. 속에 들어가서 퀴즈 되기 때문에 So I activate the quiz app here. Okay. Can you find the quiz section of the page? Okay, so you can find a quiz. Then you can find the quiz tab here, and then you can find the quiz one here. So you can just click this link, and then you can post your answers on the Blackboard. Okay, I will show you. I will show you. 공부해요. 그냥 봐도 돼요. So you can record your slide. Okay. So this is open book. Okay. Open book. Your phone, please. You can access report. Huh? So I will close the exam quiz link at 11:05. Huh? Everyone is done. It's okay. So please submit the please uh, click the submit button. Okay. So everyone is done. It's okay. Okay. So 5, 4, 3, 2, 1. Okay. I will close the exam link. Okay. Okay. So the exam is unavailable now. But not not exam. It's a quiz. Okay. So actually, it's not serious. So it's just a pop quiz, and then actually the portion is very small. Okay, so don't worry about that. The result. Okay, then actually, we will take the exam in the maybe the last week of the April, right? So please be prepared for the mid exam, right? So then what's the answer? What are the answer? That's this one, the 1A abstraction, right? And then P, it's a discovery, right? And then 2. So actually, so as a computer engineering student, then you need to be familiar with the range of the 8-bit data. Okay? Unsigned 0 to 255, right? It's 8-bit. It's unsigned 0 to 255, right? So we can represent the 2 to 8 different numbers using unsigned number system. So we use the 0 to 55. So 2 to 8 minus 1. And then those complement minus 128 to 127, right? So it's so actually in our computer system we frequently use uh, uh, 8-bit, so it's a byte data. So please be familiar with the range, the real range of a number. Okay, so it's a very simple question. Those are very simple questions. Okay, so actually I want to check the some attendance, really, real attendance of the students. Okay, so now we will learn about the Karnaugh map, and then actually Karnaugh map is the graphical approach for optimizing Boolean equations. So we learned how to optimize Boolean equations. So we can, as I mentioned, we can use axioms or theorems to optimize Boolean equations. But sometimes, so we can sometimes it can be a little bit tricky. Okay, so which means that firstly we check the some equation, and then we need to decide which theorems, so which axioms can be applied to the Boolean equations. So we can use the some different way for optimizing Boolean equations, and then this is kind of graphical. So which means that we can just use some, how can I say? So it's a graphical approach for optimizing Boolean equations. So it's a map, okay? So, and then Karnaugh is the name of a scientist. It's a Karnaugh map. So we learned the Boolean equations can be optimized or minimized by combining terms. Okay, so I believe you can memorize this Boolean theorem, right? So actually, this can be very frequently used for optimizing or minimizing Boolean equations, right? So it can be represented like the A plus A bar, right? And then we can change this to the 1, right? So A or A bar is equal to 1. Then it means that P multiplied by 1 equal P. So what can we observe? We can observe that in this combining theorem, so we can remove, a term A in the equation. So which means that we can reduce the number of terms in the Boolean equation. So we can minimize the Boolean equations. So actually, Karnaugh map exploits this theorem, the combining theorem, for optimizing Boolean equations. So actually, so it's the example. So this is the truth table. So we learned about the truth table, and then in the truth table, we just list the all possible input combinations, and then we can define the output result by input combinations. So in order to use Karnaugh map method, then we can just allocate input and output like here, so the 2D dimension, then like the 0. You can start with, so you can find the input combinations A, B, and then input C here. So, and then we can just list the input combinations of A, B, like the 0, 0, 0, 1, 1, 1, 1, 0. So you can observe that it's not 1011. It's not, right? So when we list the input combinations, like the two input combinations, it should be 0001, and then next is the 11. You have to use the Karnaugh map, not 10. So and then the next one is the 10. Okay, so this is very critical, right? So sometimes the students can be confused that, oh, the order is the 00011011, but actually we not use the Karnaugh map, then we need to use the 11 first. Okay, so this is very critical. Then C has only one, so this is C has only one input, so it's 01. Also, it means that this is the output of 0000, because this is A, B, and this is C, so this is the 000, and then input combination is this is the 010. Okay, so each element represents the output of this logic based on the input combinations, right? So I mentioned that this is the 000, so 000, the output is 1, so we can just write 1 here. Okay, and then, oh, this is the yeah. So it's a 001. So 001 this is the 001. So then, oh, output is 1. Then we can just write down 1 here in this element. So common is that, so we can just list the input combinations of the horizontal direction and then vertical direction, and then so we can make some outputs in this 2D dimensional rectangles. Okay, 2D dimensional matrix. Then we can just write down the output values. Okay? Then how can we optimize the equation? Okay, so this is the example. So this is the example. So this is another example. Then you can find the truth table here, and then this is the Karnaugh map based on this truth table. So you can find the output is 1 here. So which is, so this is 1 and this is 1. Okay, because this is the output of the 000. This is the output of 001, and then all other outputs are 0, right? 0000000. Then how can we minimize? How can we optimize these terms? So if we just represent Boolean equations using this truth table, so we can find the minterms here, minterms that they can make output 1, right? So what is the Boolean equation? So y equal, so we can select this minterm. So this is the A bar, B bar, C bar. And then also we can find another minterm that makes output 1, right? So plus is or A bar, B bar, and C. Right. So this is the Boolean equation using the SOP form, right? And then it can be optimized using the combining theorem, right? Because we can find the common part here. Okay, this is the common part, and then we can find the C bar is here, C is here. So in this case, we can remove C, right? So A bar and B bar. Okay, so by doing this, we can optimize Boolean equation. So actually, Karnaugh map explores this combining theorem. So how? Because in the Karnaugh map, we can find 1, 1, So this value is 1 and this value is 1. So which means that for these elements, the outputs are 1. So in this case, we can just merge these elements. Okay, so one here and then one. So this is the 1 and this is the 1, and then we combine these elements, and then then we can remove C here because C is 0 and C is 1 here, right? So you can just use this term like the A bar, B bar. So do you understand? In the Karnaugh map, we can make a rectangle like this by merging the multiple elements, right? Like this. And then in this case, for this column, so actually C is here, and then we can find the A column for this matrix here, and then it means that, so for this column, the input A is 0, and then input B is 0. So we can just represent the Boolean equation for Y is A bar and B bar. So basically, a Karnaugh map use the combining theorem to minimize the Boolean equations. Okay, but we can just use the graphical approach. Okay, not by using Boolean theorems. So you can use the graphical approaches to minimize Boolean equations, optimize Boolean equations. Okay. So this is another example. So this is the truth table. Okay. So we can just build this Karnaugh map using the output. Okay. Then how? So we can just use the order of truth table, right? So it's 0, 0, 0. Okay, because the C is here, and then 1, 1 is here. So where is the location of this 1, 1? It's 1, 1, right? And then, so we need to be cautious because this is in the truth table, this is the ABR 1 and 0 respectively. So we need to fill this column, right? For this output, do you understand? So it should be 0, 0. So because the order is different. In the Karnaugh map, the order of this AB is different from the order of truth table. So you need to be cautious. So sometimes if you just write 0, 0 like here, then the output will be incorrect. Okay, it should be 0, 0 and 0, 1. So 0, 1. So we can fill the output of we can build Karnaugh map using the outputs of truth table, right? Then how can we combine? How can we combine the ones? Okay. So I mentioned that in order to apply combining rule, then we need to merge the neighbor elements in the Karnaugh map. And how? Firstly, we can merge these terms, right? Then next, we can also merge these terms. It's okay. So, the 1 is included by this circle, and then this 1 is also included by this circle. It's okay. So we need to make the larger circle, the possible larger circle. So you may think that, we can merge it like this, and this is 1, also can merge it like this. But if we just use the smaller circle, then it's not optimized. So we need to use the larger circle. So the possible larger circle for merging Karnaugh map elements. Okay, elements in the Karnaugh map. So this circle represents the, so you can find that this is 0, 1, right? Then C is 0 and 1. So we can remove C for this circle. So this is the, this circle represents the A bar and B, right? How about this circle? So if we just check this circle, then C is 1, right? C is 1. And then, you know, for this circle, the A is 0, and then A is 1. So it means we can remove A for this circle, right? Because A is 0 and A is 1. So two different values. Then by using combining theorem, then we can remove A. Then how about the B? B is 1. So this circle represents the BC. Do you understand? So the optimized output Y is the A dot B plus B dot C. Okay. So do you understand? So if we use the smaller circle like here, then we need to use the A, B, C. But if we use the A, B, C, then we cannot remove A. So that's why we need to use the larger circle. And then it's okay. So the element on an element of a Karnaugh map can be included by multiple circles. Okay. So this is the optimized Boolean equation using Karnaugh map. So this is what I did. So these are some definitions. So actually we already know about the complement and then literals and then implicant, the product of literals. And then also we can define prime implicant. The prime implicant means that implicant corresponding to the largest circle in a Karnaugh map. Karnaugh map is also called the K-map. Okay, Karnaugh map. Okay, so these are rules for applying Karnaugh map. So firstly, everyone, the result one must be circled at least once. Okay, it can be circled multiple times. Okay, so as I mentioned, in order to make the more optimized result, we need to use larger circle. Okay, so if we use the smaller circle, it's not optimized. But you need to remember that every result one must be circled at least once. Okay, so it means that circles need to include all ones in the Karnaugh map. And then each circle must span a power of 2. So this is not possible, like 1, 1, 1. Okay. So what's the problem? So this circle includes the 30 elements, but it's not allowed. It's not allowed in the Karnaugh map. Thus, each circle must span a power of 2 is 1, 2, 4, or 8. Okay. 3 is not allowed, and 6 is not allowed. Okay, each circle must be as large as possible. But this is important. So in the exam, so actually midterm exam will include the Karnaugh map questions about the Karnaugh map. But some students just miss this point. Okay, we need to use the larger circle. So as large as possible. The circle needs to be as large as possible. Okay. So like this. So 111. So we need to use the larger circle, not this one. Okay. The result is actually the result is but it's the same, but it's not optimized. And then another, so this is important. So okay, and then another point is a circle may wrap around the edges. What does that mean? Sometimes students can be confused. So it's like this. So 1 1 0 0 0 0 1 1. Okay, it's a color map. So A, B, and then this is C. So how can we merge ones in this color map? So you can think that, oh, we can merge this one and this one. Oh, it's okay. So the Y is A bar, B bar, plus this is so 0 0 0 1 1 1 1 0. Also A B bar, and that's it. Oh, is this equation optimized? What's the problem? We can also apply combining theorem for A. So what's the optimized equation? This is E bar. So what's the problem? So we use Karnaugh map. So we use Karnaugh map for optimizing Boolean equation, and then if we just use the Karnaugh map rules for until this line, then this is okay. But we also observe that this equation can be optimized further, right? Is it because in the Karnaugh map, even though this column is separated from this column, but we can think that this edge is connected to this edge. Do you understand? So we need to merge like this one and this one. Okay, so you need to think that actually in a 2D plane, so this column is separate from this column, but we need to think that this edge is connected to this edge. So which means you have to make largest rectangle or largest circle, then the circle need to include this one and this one. Okay. So circle may wrap around the edges. This is very important. So sometimes the students can be confused because these columns are separated, but you think that this column is connected like the cylinder. Okay, so as I mentioned, this edge is connected to this edge. Okay, so we can make the larger circle like here and here. Okay, so that's the example. So this is the point for Karnaugh map. Okay, so so firstly we need to know that this is 0 0 1 1 1. Okay, and then 1 0. How can you build the Karnaugh map here? So we can start from this one. So in the truth table, so A B is 0 0. So we can firstly build this column, right? Then how? It's 1 0 and this is 1. So also if you see that is CD column, then you can find that this is 0 0 0 1 1 1, right? Okay, so this is 1 and then this is 1. Then we can start from the 0, 1. So this is the 0, 1, 1, 1. So 0, 1, this one, 1. Okay, because this is 1, 0. Okay, so you need to be cautious. And then this is 1. How about this one? You need to feel this color, right? So 1, 1, 1, 0. So 1, 1, 1, 0, right? And then lastly, this column 0, 0, 0, 0, 0, 0, 0, 0. So actually 0, 0. Okay. Because they are all zeros. Okay, 0, 0. So we can feel the result, the result of the truth table, the Karnaugh map like this. Then the next step is we need to find the largest circle as possible that can merge ones. Okay. Then what is the largest circle in this Karnaugh map? So we can just easily find this one, right? So it's a rectangle, and then also it includes 4 elements. So it's okay, right? And then what is the another largest circle? Another largest circle is this one, this one, this one, this one. Okay, so I mentioned this edge is connected to this edge. Also, but also for the CD, this edge is connected to this edge. Okay, so it means actually you can find the 1, 1, 1, 1, 1, 1 here. So, but in the real plane, this is connected to this one, and this is connected to this one, and then blah blah blah. So actually we can make the largest circle for this one like the one here, 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 and here. Okay, so we need to be cautious. And then the another possible largest circle is so we cannot find any circles that can include 4 elements here. We can find another largest then we can find we can merge here, and then also 1, 1 we can merge here. Okay, so every one is included by circles, right? Then we can write the equation. How about this circle? What is the equation of this circle? This circle, so A is 0, and then C is 1. And then, so in this circle, the B is 0 and 1, and then D is 1 and 0. So which means that we can remove D and D, right? Do you understand? So for this circle, so A is 0, this is A bar, and then C is 1, the C. Then how about this circle? This 2, 2, 2. What is the equation of this circle? The equation is, so in this circle, the B is 0, right? But A is 0 and 1. So which means that we can remove A by using combining theorem, right? And how about the C and D? So in this circle, the C is 0 and 1, right? So we can remove C, but D is 0. So what is the equation of this circle? This circle is the I forgot. It's B bar and D bar, right? Okay. So how about the circle? So we can apply the same rule. So we can make the equation for this circle and then equation for this circle. Okay, so is result. So this is the result, the final result. So actually, if you see the this slide, you can find that you can find how the one is mapped on like this. Also, this is the final result. So you can find the equation mapped to the color of the circle. Okay, so the green color, this is the equation of this green color, the large circle, and then the is the purple color. The purple color is this circle, the equation for this circle. Okay, so this is the optimized equation by Karnaugh. Okay, so actually, if we use the Karnaugh map, then we can easily apply the combining theorem graphically. Okay.
Can you show the calculation for the green one?
What? Equation for the green one? So this is the equation for the green one, right? What's the difference? So this one.
How you get E or C?
Parse. What do you mean, parse? So this one?
Yeah, how do you get A or C?
So as I mentioned, so if we just consider this circle, so you can find that so AB includes the 0, 0, 0, 1. So this is the AB, right? So if you see that this combination, then you can find that B is 0 and B is 1. So it means we can reduce B. So it is similar to the A B plus A bar B bar plus A bar B. So this is the A bar B bar plus B. Okay, and then this is, you can reduce, you can remove. Okay, and then how about this part? So this, if you see this part, then CD is 1, 1 and CD is 1, 0. So it is the CD plus CD bar. Okay, so we can reduce D. So this is the C. So this is the A bar, and then for this direction, this is A bar, and then for this particular direction, this is C. So this is becomes the A bar C, right? Understand? Okay. Okay, so this is the Karnaugh map. Okay, and then you can also use the don't care. So actually, these are rules we learned about the Karnaugh map, and then you can also find the additional rule circle or don't care is X. So as I mentioned, we can use X to represent don't care in the Karnaugh map or truth table, right? And then only it helps. So don't care means that the output can be 0 or 1. Any output can be any values like 0 and it can be 0 and it can be 1. So we can use the don't care in the Karnaugh map, but only if it helps. It helps minimize the equation. Okay? What does it mean? It can be 1, it can be 0, but we can include the don't care if it is helpful for optimizing equation. If not, we don't need to include don't care because it can be 0. So example. So this is the example. So you can find that in the truth table, you can find axis here. So where output axis here. So it means that it's don't care. So it represents the output can be 1, the output can be 0. So it's like so I can eat lunch, but I don't care if I cannot eat lunch. It's like this. I understand. Anyway, so I can eat lunch, or I don't care if I cannot eat lunch. So because it's called don't care, right? So it can be 1, it can be 0, but then by we can allocate the output of this truth table to the Karnaugh map like this. So you can find the many axes here. Then, how can we apply circles to the Karnaugh map? So, how can we find the large circle? The largest circle as large as possible in this Karnaugh map. Firstly, so I mentioned that the Karnaugh map can include the power of two elements like 1, 2, 4, 8, right? Then if we just use don't care, then firstly we can find the largest circle like this. Right. So we can think that this x is the 1, right? So we can firstly define this circle that includes 8 elements. How about this one? We can also include the large circle right here. Okay. It is not possible because of 0. Okay. This large circle cannot include 0. So we can also define the large circle that includes the x. Okay. So here, here, and then here. Okay. So in this example, the circles include all x's because we can think that our x can be 1. But sometimes if x is not helpful for optimizing the equation, then we need to exclude this x from the Karnaugh map. So like this, we can just apply the okay, this is not good example. Okay. So as I mentioned, so we can, we don't need to exclude this, but this actually, we don't need to include this x because all x's actually these are already included. So we need to, so actually, the x is here, but we don't need to include this x. Okay? Actually, we don't need to make this circle. Okay, this is the result. So x can be included in the large circle, and then like this, and then this x is not included. So this is the optimized Boolean equation by this Karnaugh map. Okay? So we can use the don't care in the Karnaugh map. Okay? So so this is, so I will stop here, and then thank you for your attention, and then see you in the next class. Come down.